All right, so we're going to discuss related rates, which is another application of derivatives. And we're going to say this basically, mathematicians aren't very creative with their name, shall we say. So related rates describes exactly what it means. So we're going to take a rate of change. So there's the rate, and we're going to relate it to another rate. And this WRT just stands for with respect to. So if we're allowed to, there we go. We'll just write in, just so you know what it means with respect to. And essentially what we're going to do is we're going to take the derivative of a relationship, so that's the related part, of one variable to another. So we're going to try to figure out what is the relationship between y and x, or the volume and the radius, or something like that. And we're always going to take the derivative with respect to time, and that's very important. So everything is going to be with respect to time. And generally speaking, you're going to be given a rate, and then you're going to be asked to find another one. So if we look at some examples, what we're going to do is we're going to just look through some representative examples of this. And as we do, we'll point out some things along the way. So here's a representative sample. It says a spherical snowball is melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing when the radius is 5 centimeters? So to tackle this kind of problem, the first thing we want to do is identify the rate that we're given in the question. So you can see there's the rate. That is the rate of volume. And you identify the rate, first of all, by understanding that it's per minute. So that tells me that it's a rate because it's something with respect to time. And then it says up here that it's decreasing. So that means something as well. That's telling me that it's negative. It's going down. And it's the rate of volume. So what we can do is we can say that it's dV, the derivative of volume with respect to time, dt. So this 1 cubic centimeter per minute is dV by dt. And then it's going to ask us at what rate is the radius decreasing. So now we're talking about, we want the radius, we want the rate of the radius, okay? So we want dr by dt. And then it tells us that we want that when the radius is 5 centimeters. So what you'll see in every related rates problem is this particular spot that we want to look at. It might not be given as a radius, it might be given as a height, it might be given as a particular volume, but it's always going to give you a particular time or place or value at which we're talking. Because as the snowball melts, the rate at which the radius decreases is going to be different if the volume continues to decrease at 1 cubic centimeter per minute when the radius is really big versus when the radius was really small. So if you think about a snowball, if it's a really big snowball, the radius isn't going to change much if it's just losing a cubic centimeter of volume. But if it's only 1 cubic centimeter of volume left, then obviously the radius is going to go to 0. So the rate at which the radius is changing or decreasing is going to increase. It's going to get bigger as the radius gets smaller. So we're talking when the radius is 5 centimeters. And then up here, we also see that it's a spherical snowball. So what I like to do when I approach these questions is, first of all, draw a picture. Okay, just draw what it looks like. So it looks like a sphere. Now I'm cheating a little bit because that's from the smart art up here, but it's a sphere. And a sphere, we know, if you draw from the center to the outside, has a radius, and we're going to call that radius r. And then it has a volume. So we know, based on what we just discussed, that we have dV by dt, that it's negative because it's decreasing and it's 1 cubic centimeter per minute. We know that we're talking about when the radius is 5 centimeters, and we know we want dr by dt. So the issue is now to figure out what is the relationship between these two variables. What is the relationship between volume and radius? And if you know the volume of a sphere, you know that relationship. If you don't know, that's the relationship. The volume of a sphere is 4/3 pi r cubed. So then what we do with that is we take the derivative of it with respect to time. So that means it's implicit differentiation, which we've talked about before. And so this v, when we take the derivative, it becomes v prime because it's a variable not that we're taking the derivative with respect to. In other words, we're not taking the derivative with respect to volume, we're taking it with respect to time. And so we have to put dv by dt if you're using Leibniz notation, or v prime. And if you're using Newton's notation, the same thing happens with r. So the derivative of r cubed, we're going to treat as a chain rule. So it's going to be 3r squared, but then multiplied by dr by dt, or r prime. So if we take the derivative, this is what it looks like. dv by dt, that's the derivative of volume. The 4/3 and the pi are constants, so they simply stay there. And then the derivative of r cubed is a chain rule. We do the power first, so it's 3r squared, and then we multiply by dr by dt. So then what we do is we're looking for this. That's the part that we want. So if we isolate it, we can get rid of the 3's. We already showed that, but I'll just do it again. So I have 4 pi r squared dr by dt is equal to dv by dt. I know this. This is -1. And I know this, it's 5. So what I can do is I can plug those numbers in now. And so what I end up with then is this. -1 is equal to 4 pi times 5 squared times dr by dt. Now 5 squared is 25, and 25 times 4 gives me 100. So I end up with 100 pi, and then I just divide by it. And I end up with my answer. Dr by dt is -1 over 100 pi. And the unit comes from the measure of the radius was in centimeters, so it's 5 centimeters, and then it's per minute because that's the time unit we're using for all of our rates. It's consistent throughout. So if the volume's changing per minute, so is the radius per minute. And that's it. That's how you do a related rates problem.